Sometimes I hate software. Okay, so Lab 2, mistakes and errors and kinds of measurements. All right, so two kinds of error that we talk about, are the two kinds of ways of measuring these things. We talk about precision, and we talk about accuracy. Okay, these are two different ways of talking about error. So precision is about how closely grouped your measurements are. Whereas accuracy is how close your measurements are to the correct answer. So in terms of the kinds of error we're talking about, precision is about noise or random error. Accuracy, we're talking about bias or systematic error. Okay. So noise or random error, we're looking at error that is just all over the place. It's not in a single direction. Accuracy, we're dealing with bias or systematic error that is constantly shoving us off in a particular direction. So an example of noise would be, just that when you're trying to talk to someone in a crowded, noisy room, you have a whole lot of sound information coming into your ears. You only want to catch a small amount of that information, the person you're talking to, so you have to try and filter out the random crap. When you're in the lab, say you're trying to weigh a small amount of something on a particularly sensitive balance. Random breezes moving through the room can push on the pan of the balance, push it up, push it down, and thus you'll get the numbers fluctuating, jiggling around, and it'll be more difficult. That's an example of noise. So the way you deal with these things is it's going to be different based on the different kinds of error. So systematic error, bias, it's constantly being pushed off in one direction. An example of that, if imagine you're playing darts, if there's a fan on one side of you, it'll constantly be blowing your darts off in just to the one direction. Okay? And target practice, if you play around with guns, that's known as windage, because of the wind. So the way you deal with these is different. So you deal with noise or random error through insulation, isolation, or just take multiple measurements. Okay. If you look at the balances in lab, once you get there, you'll see that they come in these glass boxes with sliding doors. That is so that you can put stuff on the balance, you close the door, you wait for it to settle down. It literally isolates the pan from those random breezes. If you're trying to measure temperature, then it really is literally insulation. You are trying to keep outside temperature things from affecting the experiment. Okay. Bias or systematic error, you deal with that through calibration, okay, where you use a known quantity to adjust the thing you're measuring. You have, say, a set of weights where you know exactly how much they weigh, and you can tell your device, okay, this is how much you should be measuring at this point. A single point calibration would be if you only measured the one thing. You can do a 2-point calibration, so you get sort of a line, or a 3-point, 5-point. The more calibration you do, the better off your machine is going to be, but the more time it takes. So, it's just, how long you want to spend on that. All right. So the way we visually represent precision and accuracy, I'll go ahead and switch to another page. This is the most popular diagram in the world. All right, so is it precise? Yes, no. Is it accurate? Yes, no. All right. So we have our target. And we have the correct answer here in the middle. If our measurement is both precise and accurate, precision means that the measurements will be closely grouped together. Accurate means they'll be centered on the correct answer. If it is accurate but not precise, it'll still be centered on the correct answer, but you're going to have a lot more noise. Thus, you'll have a lot more scattering far away from the center of the target. If it is precise but not accurate, inaccurate means it is off target in one particular direction, but precise means that the answers are still closely grouped together. If it is both imprecise and inaccurate, it'll be off in one particular direction, and you'll have a lot of random noise in the thing. So we want our answers to be both precise and accurate. We want to eliminate both kinds of error as much as possible. No matter what, though, there's always going to be noise. Hopefully you can eliminate bias, but there will always be noise. You're always going to have to take multiple measurements so that you can, find the average, the center of your group of measurements. Yes. Okay, so we also have ways of measuring and talking about how precise we are and how accurate we are. Okay. So for precision, we have deviation. Okay. So precision, we're talking about how close our numbers are to one another. Okay. So deviation, we represent it in mathematical terms like this. X sub I means we're talking about a particular measurement. X bar means we're talking about the average. Now, for precision, because we're talking about random error, we're talking about noise, we don't care about which particular direction it is wrong. All we care about is how far off it is. Thus, we have these straight lines here representing absolute value. So if it's negative, you just turn it positive. That's all that means. So the absolute value of 5 is 5. The absolute value of negative 5 is also 5. So deviation is just how far is every measurement, how far is each measurement, I should say, from the average value of all the measurements. Okay. And then we have percent relative deviation, because the fact is that, the measurements you're looking at, they could be very, very small or very, very large. But that doesn't necessarily tell you, how good or bad your precision is. You have to say how good or bad is your precision relative to the measurement you're making. If you're off by 5,000 miles, that's a hell of a difference if you're trying to drive across Greenville. But it's really, really awesome if you are trying to aim at another star system, which is going to be billions of miles away. So that's why we use percent relative deviation, which is going to be the deviation divided by the average and then multiplied by 100%. So that gives you that puts the deviation in terms of the measurement itself. So that way you know how far off you are with respect to what kind of measurement you're taking. So that is how we talk about precision. How precise are we? we talk about it in terms of percent relative deviation. You want a very, very low percent relative deviation. You want to eliminate noise as much as possible. Now, accuracy looks very, very similar. Let's see. Nope, no questions. Accuracy looks very, very similar, except instead of deviation, we talk about error. Okay? So for error, we have, or sorry, for accuracy, we have error, which is going to be xi minus xt. Okay? So in that case, we are comparing the individual value to the known true value. So this right here is the absolute error. And notice that now we do care about whether our measurement is positive or negative. We need to know how far we are off in what direction. Okay? But again, absolute error is less valuable because, you know, again, 5,000 feet off or 5,000 miles off, you know, that could be good, could be bad. So instead we talk about percent error. So individual measurement, true value divided by the true value times 100%. So in order to talk about how accurate our measurements are, we put it in terms of percent error or percent relative percent error, you know, however you want to call it. And again, we want our percent error to be as low as possible. We want to eliminate bias from our measurements. We want our measurements to be as close as possible to the true value. So that's why you calibrate. Okay. When I was working for a pharmaceutical company, 5% error was considered the bare minimum acceptable. That was considered just kind of doing an okay job, but crap, you need to get better at it. My boss, who had been doing that stuff for 20, 30, 40 years at that point, he was able just bang, bang, boom, knock it out with, you know, just a 1% error. It was kind of humbling. All right, so now this particular lab, what are we measuring? We're measuring density. Okay, so density is the measure of mass over volume. How much matter is there in a certain amount of space? Different materials have different densities because some of them have, you know, the atoms and molecules packed together really, really closely, or they could be a really, really loose packing. You also just have different sized atoms. You know, some atoms are heavier than others. So you get different densities for your different materials. So in order to measure your density, you're going to have to measure the mass of your object. You're also going to have to measure the volume of your object. Mass is relatively straightforward. You just go ahead and put that on a balance, and you measure that. Woohoo. Volume is where things get a little bit tricky. So let's go ahead and change colors again because I want to keep it visually interesting. So for regular objects, measuring volume is fairly easy because regular objects have regular shapes, and we know, you know, the formulas for those. You know, so for example, a sphere, volume equals 4/3 pi r cubed. So all you need to do is measure the radius. And how do you do that? You take a caliper and, you know, you measure the diameter, divide it by 2. You know, diameter equals 2 times the radius. Just, I'm throwing a lot of formulas at you because you're going to need to know these various times in this class. So in order to measure the volume of a sphere, you just need to take the calipers, you know, pinch them down on the thing, and they'll tell you. It's a caliper is a, actually I can probably caliper, bring that up. Yeah, so here's, you know, pictures of calipers over there on the right. It's literally just a thing. You bring it down, you pinch it, and it'll tell you how wide the object you're pinching is. Okay, bang, bang, boom. For say a cube, you know, it's again fairly straightforward. You know, just volume is equal to the cube of the edge length. Okay, so you just need to measure how long the edge of the cube is. For a cylinder, the volume is, pi r squared h, where, h is the height of the cylinder and r is the radius of the circular end of the cylinder. When this lab is performed in the lab, the materials you're working with are various kinds of metals arranged in cylinders. So that was, something you needed to have. But not everything comes as a regular object. How can you measure the volume of, this chunk of random crap, right, that doesn't have a particular shape? Well, for that, you need to use what's known as volume by difference. So volume by difference is when you take advantage of the fact that liquids exist. Okay, so you get yourself a graduated cylinder, and it's got markings on it that let you measure volume, and you put some amount of liquid in there. You measure. Remember, you measure depending on the liquids you use, it might be the bottom of the meniscus, it might be the top of the meniscus. In the lab, it's almost always going to be water, and thus you would measure the bottom of the meniscus. And you would get a volume, say 43.2 milliliters. Then you go ahead and you drop in your object. And it's going to displace some of that water. It's going to give you a different measurement. The water level is going to go up, and it's going to go up by the volume of the thing. So you drop in your object, and suddenly you have 50.1 milliliters. Okay. That means that volume of your object is equal to 50.1 minus 43.2 is going to be 6.9 milliliters. Okay. So that is an example of volume by difference. Now there are lots and lots of different ways of measuring the volumes of liquids. You have graduated cylinders, you have beakers, you have burettes, you have pipettes. Not all devices capable of measuring volume are good. A beaker, for example, a beaker being this guy right here, beakers are crap. Okay, they have a thing on there so that you can get a rough idea of what the volume is, but you do not use those to measure volume. A beaker is just meant to hold stuff. Graduated cylinders are a heck of a lot better. They do a much better job of measuring volumes. But pipettes are even better than graduated cylinders. The limitation with those is they're harder to use and they're smaller. They typically only hold they hold a much smaller amount of liquid. The very best is your burette. That is not very mobile though, and it's not really meant for dispensing a particular amount of liquid. Instead, it's meant for dispensing liquid and then telling you how much you've dispensed when you're done. That's when you're doing stuff with reactions, for the most part. At least that's how I have used it in the past. Pipettes are what we use when we want to dispense a certain amount of liquid. Burettes are what we do when the liquid is part of a chemical reaction. Very often. So burettes and pipettes are the best for when you want a particular volume, when you want to be really good about the volume. A graduated cylinder is when you want an easier method of measuring. Never use a beaker. Never, ever. Also, remember, when you are taking a measurement using a device, you always estimate between the last two lines. So a graduated cylinder, the smallest marking will typically be 1/10 of a milliliter. So you would then estimate beyond that. So these numbers here would not be right. So say this line, it goes up to about 43.2. Oh, actually here, let's look here. This measurement here, so you see, yep, you can see it. The beaker's bad for measuring because first off, the lines are very far apart, so it's not very precise, but also they're just not, they're not really intended for measuring, K-poop. So they just, they're not made for measuring, so they're just very inaccurate. They'll give you a rough idea of how much liquid is in there, but they're really not intended for measuring. It's like trying to use a saw to measure something. I mean, the saw has a length, and you could use it for that, but you wouldn't do that. All right, so here we have a graduated cylinder, 43, 43.1, 43.2, 43.4, 43.5, 43.6, 43.7. No, that's 43.6, 43.7. You read the bottom of the meniscus and... Okay, so we'll go with this one. 91, 2, 3, 4, 5. And then the meniscus, yep, it looks like it falls between 0.5 and 0.6. So 95.5. Wherever the smallest line is, remember to estimate one beyond that. So this graduated cylinder here measures to a single milliliter. So your measurement will go beyond that by 1 decimal place. Okay. If you have a better graduated cylinder, this one is the one that goes to 1/10 of a milliliter, so your measurement would have to go beyond that by 1 decimal place. So your measurement would go to the 100th of a milliliter. So 43.1, 2, 3, 4, 5, 6, 7, and that looks like it's sitting directly on the line, so it would be 43.70. Hence what they're saying there. So just a reminder. That's if you're using an analog device like this with lines marked on it. If it's an electronic device, just write down the numbers they give you. In terms of accuracy and precision, the uncertainty in your measurement, the error in your measurement is contained in that last digit. You're very confident in all the digits until you get to the last one. The last one is where it gets a little fuzzy. That's how that works. All right. A volumetric pipette. Unfortunately, you don't get to use a pipette in this week's lab because you're not in the lab. But pipettes are incredibly common. You're going to be, when you get into the lab, it's just this long, narrow tube. Go ahead and watch this video. You'll use a rubber bulb as the suction to draw liquid up into the tube. Remember, don't get liquid into the rubber bulb. It'll totally screw up whoever comes after you because then they'll have random crap falling into their pipette. Also, never, ever, ever turn a pipette upside down because, again, you'll get crap into the bulb. Or if you're in a higher level lab, into the pipetter. A pipetter, you'll love pipetters once you finally get to those. A pipetter makes pipetting so much easier. All right, so they're talking about density, and then you get down to the actual experiment where you will be measuring sort of the densities of different objects. So that is this week's lab. All right, density, taking measurements, accuracy, and precision. Accuracy and precision are both very popular topics to go on tests. They might show you a group of numbers and ask you, is it accurate? Is it precise? Is it one but not the other? That sort of thing. And so you will learn to judge those. Accurate means that they are all grouped near the correct answer. Precise means they're closely grouped around one another rather than widely scattered. Okay, density is also popular. And again, I want to stress, you need to be good at this sort of manipulation. Density is mass over volume. Volume is mass over density. And mass is density times volume. be good, get good at doing that sort of quick algebra manipulation. All right, that should be everything for this lab. I am going to go ahead and call it. I'm going to take a short break to rehydrate, and then I will start doing more videos for Chapter 2 for the lecture portion of the class. All right, I will see you probably